So we've learned a lot about the bonding of carbon. We've learned that we typically think of carbon as hybridized, either sp3 hybridized, so 4 single bonds, sp2 hybridized with a pi bond, or sp hybridized with 2 pi bonds. How can we use this? One way we can use this is to predict information about structure, about geometry, sort of given the bonding of the system. So for instance, this big hunk of molecule is ethynyl estradiol. It's a really important oral contraceptive, so one of the early birth control pills. So we can look at this molecule and see that there are lots of sp3 carbons, and all of those carbons probably have bond angles something like 105, right? We probably have something like a tetrahedron. So in your books, why don't you draw this molecule and then put a dot by all the sp3 carbons. I'll wait. Push pause now. Okay, cool. So let's put a dot by all the sp3 carbons. So it's everything without a double bond or a triple bond. So not these, but this one, anything that has that CH2 like that, these. Again, these wedges mean it's coming at you. The dash means lines that it's coming away from you, right? And all those are indicative of tetrahedral carbon. We don't always draw it out. We could have drawn out the wedges and dashes for this CH3, but we didn't. Okay, so I think those are all the sp3 carbons. Now, let's draw little circles next to sp2 carbons. So these 6 are all sp2. And you'll see this motif a lot. By itself, it's called a benzene ring. We'll also call it an aromatic ring. But we'll see this kind of 6-carbon, 3 alternating double bonds motif show up a lot. Just about in every drug you would ever take has something like this in it. Is that it? Yes, those are the only sp2 carbons. Now, let's draw an X next to any sp carbons. Well, that would be these. Triple bonds. How do we use this nomenclature? What good is it to us? Well, for one thing, it gives us some information about the actual 3D structure of the molecule. sp2 carbons are flat. So I know that this part of the molecule is flat, like a plate. But sp3 is tetrahedral. It's 3D. This part of the molecule is very 3D. You can kind of get a sense of that from these dashed and wedged lines. And then the sp is, again, linear. So I'd expect this thing to stick out like a stick. It's sticky, right? It's sticky and like it's sticky in that it is like a stick. It's stick-like. Here. Okay? So knowing this hybridization gives us some hint about the geometry of the system. We can also compare bond dissociation energies of these molecules. So by bond dissociation, we just mean how much energy does it take to just break that bond in half with one electron going one way and the other electron going the other way. We've mentioned the Morse potential, this idea where there's some minimum energy bond length. If I try to squeeze the atoms together, it goes up in energy pretty fast. If I try to pull the atoms apart, it goes up for a little while, and then eventually it just pops and my 2 atoms fly away at a constant energy. So again, you can think of this bond dissociation energy as this energy here. Comparing single bonded ethane, double bonded ethene, triple bonded ethyne. What you can see is that the bond gets shorter and the bond gets stronger, right? And those two things are intimately linked. Shorter bonds or stronger bonds. There must be some good way to remember that. Let me think about it. I'll keep thinking about it. Anyways, shorter bonds, stronger bonds. So essentially you've got more orbital overlap that's pulling the electrons closer together, pulling the nuclei closer together. Funny looking A with the circle over it is an angstrom. That's 10 to the minus 10 meters. So that's 0.1 nanometers or 100 picometers. Right? So I don't expect you to memorize these numbers at all. If somebody asks me how long a carbon-carbon bond is, I'm like, I don't know, about 1.5 angstroms or so. And a CH bond is about 1 angstrom. But again, you do not need to memorize these numbers. I also want to point out that the double bond here is not quite twice the single bond, right? So this isn't just 90, 180, 270. Why is that? Well, it's because this pi bond doesn't have as good of orbital overlap as the sigma bond. So pi bonds are weaker than sigma bonds here. Again, sigma bonds are stronger than pi bonds here because they have much better overlap. So maybe some of you are like, okay, this is obvious. I get that a double bond is stronger than a single bond. I get that a triple bond is strong. That's what a bond means, whatever. But check it out. Here, now I'm just comparing the CH bond. So now I'm not comparing single with double with triple. I'm comparing single CH bonds across these three molecules. And I still see a pretty big effect. So notice, as I go from single bonded ethane to this double bonded ethene, not only does the CC get tighter, the CH gets tighter. 1.1 angstroms to 1.08 angstroms. It gets stronger by about 10 kilocalories per mole. And notice that in ethyne here, not only did my CC bond get really strong and small, my CH bond got really short and really strong as well. So how should I think about this? Let's meditate. sp3 carbon. I used one s and 3 p orbitals to make an sp3 orbital. And so really that sp3 orbital is about 25% s and 75% p. That's just math. Here, sp2, 1/3 of it is s, 2/3 of it is p. And sp orbital is 50% s, 50% p. Well, we can think about S character, right? So the more S character, the more S-like the orbital is, the more slike the orbital is, the better the orbital overlap in bonds where it's going to have. Because again, remember that our first bond was a sigma bond. We said S orbitals overlap really nicely to give sigma bonds. P orbitals are the ones that overlap less well to give us pi bonds. So the greater S character we have in our orbital, the better orbital overlap we're going to have. The bonds are going to be more sigma-like, which is to say, again, better overlap and stronger. We can look at the hybridization of carbon and not only make predictions about geometry, that's going to be tetrahedral, that's going to be trigonal with 120, triangle-ish, that's going to be linear. We can make those predictions, but we can even talk about the strength of that bond. I expect this CH to be quite a bit stronger than that CH, which is in turn stronger than that CH, because this carbon is more S-like, has greater S character. So the bonds that it makes, both the carbon and the hydrogen, are going to be a little bit more sigma-ish. Better orbital overlap, shorter bond, stronger bond.